Professor Andrey Andreevich Shkalikov with his talk, Factorization of Quadratic Operator Pencils and Mandelstam Conjecture. You have 40 minutes and 9 minutes for questions. Please.
Okay. My talk will consist of 3 parts. The first part is a general one. I will speak about operator equations in Hilbert space. And the second part, in the second part, I will speak about hyperbolic pencils of the second order. And in the third one, about elliptic pencils, quadratic elliptic pencils, and Mandelstam hypothesis. So first consider equation which is written in blue, colored in blue, and here u of t is a function in Hilbert space H, and A, J are unbounded operators in Hilbert space, acting in this space. The most important case certainly is m equal to, and I mean in applications. However, the equations of the first order one can meet frequently as well. The setting of problems for such equations and the equations of uniqueness and solvability of the corresponding problems are closely related to the study of the spectral properties of the operator pencils of this form. The derivative in this polynomial pencil, the derivative in the equation which we considered before is replaced by the spectral parameter lambda. It is equivalent that we take Laplace transform from this equation, and then we come to this operator symbol or operator pencil. As I told, the objective of this talk, the main objective, first part will be general one, and actually the main second and third part is to consider 2 classes of operator differential equations, which we can call hyperbolic and elliptic. For the corresponding operator symbols, operator pencils, we save the same words. Naturally, we come to problems which are closely connected to the theory of strongly continuous one-parameter semigroups and holomorphic semigroups. So I will speak, in particular, in the third part, I will speak about factorizations of elliptic pencils, and the main result will be that the divisor actually generates a holomorphic semigroup. So I tried to do my best to be closely connected with the topic of the conference. First, we consider the classes of operator pencils, which we call standard. Assume that the domain of definition of the main operator A0 coincides with the domain of definition of a self-adjoint operator S to the power m, where S is positive self-adjoint operator. I just would like to mention that that if operator A0 is closed, then the Hilbert space, which is connected with the graph subspace of the operator A naught, is closed too, and automatically such an operator S does exist. So it's only sufficient that A naught is closed operator. And S is important for us in the future. Assume also that for the domains of the operators A, J, we have the following inclusion. The following inclusion. And moreover, certainly if A, J are closed, then automatically this means that the operators A, J as to the power J minus A are bounded. So if AJ are closed, then inclusions, which these inclusions guarantee that these operators are bounded, but if they do not admit closure, we have to assume this condition in the addition. Actually, what does it mean, this condition? It means that the middle term in the equation, are, if we, actually AJ are differential operators, and derivative with respect to time t, also derivative. And what does it mean? It means that the middle term in these equations, the order of derivatives of these middle terms do not exceed m, the order of the equation m. A standard pencil is said to be Keldysh pencil if it has much more simple form. A naught is self-adjoint operator to the power n, positive self-adjoint, plus k naught with k naught, where k naught is compact. Am is identity plus compact operator, and Aj are compact operator times to the s times to the s to the power m minus j. Further, I assume that the k of s is finite order operator. Finite order operator. It means that the eigenvalues of S admit estimates from below of this type with some p greater than 0. The larger is p, the better. So, in other words, Keldysh pencil is a compact perturbation of the simplest pencil s to the power m plus lambda to the power m times identity operator, with s, which is strictly positive and has the finite order. Let us define the space Hm equals the domain, which coincides with the domain of Sm. This is a Hilbert space, since the operator Sm is closed. And define the intermediate interpolation spaces in the usual way. interpolation between HM and H, with theta between 0 and 1. In particular, Hj coincide with domain S to the power j. Consider those spaces. So the first space is the topology of this space is stronger than this one, because here -1, here -2. And the last space is with the weakest topology, H zeta. If lambda k by k is an eigenvalue pair of the pencil A of lambda, it is yk is the eigenvector corresponding to the eigenvalue lambda k, then uk of t, which is the exponent multiplying by the eigenvector yk, is the solution of the equation which we consider from the very beginning. We'll call these UK elementary solutions. So if lambda k yk is an eigenvalue pair, that this UK is elementary solution of the differential equation. We can write out elementary solution corresponding to Jordan chains of pencil when we have not only eigen for but also associated vectors. Of brevity, we assume that all eigenvalues of the pencil A of lambda are simple. Otherwise, it will be very clumsy and very technical. Consider the trace operator corresponding to the Cauchy problem of equation 1. So, to the solution of U of t, we take the trace, we apply the trace operator. Here, psi is a fixed point on the real axis, and UK of psi derivative of psi k is, I have to put here, certainly not here, and here UK is a m -1 derivative of UK. So these vectors actually belong to the space which we defined before, provided that U of t belongs to some functional spaces. I will to some functional spaces. Let me. In particular, the trace theorem says the following: that the trace operator is bounded from the Hilbert space W abstract Sobolev space if U of t belongs to the abstract Sobolev space WM2, then this trace operator is bounded. For if we take C equals 0, then the trace coincide with both YK equals yk lambda k yk and so on. These vectors in this page, H beautiful, which I defined before, are called Keldysh derivative chains. First theorem, let the spectrum of the standard pencils be discrete. It is consists of isolated eigenvalues of finite algebraic multiplicity. In particular, if the operator S, it is true in particular if the operator S minus 1 is compact. In this case, the traces of elementary solutions yk form a minimal system in the space H beautiful zeta for all zeta belonging to 0, 1, to the interval 0, to the segment 0, 1. And it forms a complete system in these spaces, provided that the pencil A of lambda is a Keldysh pencil. In particular, the system of the traces of elementary solution is minimal and complete, provided that A of lambda is Keldysh pencil in the space. Zeta here I took equals 1/2. And this space 1/2 corresponds to the space of strong solutions U of T belonging to this Sobolev space with a norm which is defined in the following way. We apply the unbounded operator to U of T and take derivative in the usual space, and then integrate and take, as usually, the square root. This theorem says that we can find an approximate solution of the Cauchy problem of the equation 1 in the spaces H zeta. Namely, for any initial data U0 belonging to H zeta, and for any epsilon greater than 0, we can find a finite linear combination of elementary solutions. Certainly, the sum is a solution. Each elementary solution is a solution, and its linear combination also is solution. And the trace operator from this equation U of T minus U0 initial data will be less than epsilon. So we can find an approximate solution of the equations which we defined from the very beginning. However, the function U of T may grow as T tends to infinity, even if the spectrum of the pencil A of lambda lies in the left half plane of the convex plane. In this case, we can certainly not can. We can guarantee the but we cannot guarantee certainly that the solution is not growing when T tend to infinity with their derivatives. We can guarantee this property only in the case when the traces Keldysh derivative chains form an unconditional basis or Rees basis in the space of traces. Even more so, we cannot state the existence of exact solutions of the Cauchy problem of the equation 1. In particular, the Cauchy problem for Keldysh pencil of order M greater than 2 is always incorrect. It's always incorrect. The minimality of the Keldysh derivative change in the space of copies of HM topology of the space is more strong, but not pointing out the explicit form of the orthogonal system was proved by Keldysh. Actually, we prove the minimality not only in this space, but in spaces with weaker topologies, and this is more strong result. Lemma, which was proved by Keldysh in 1951, and it was announced, and then in 1971, it was proved in details. The main part of the Lorentz representation of the resonance of the pencil in neighborhood of the pole lambda equals lambda naught has a representation of the form. And here you see the sum is finite. The sum is finite, and here y naught, y jk, y jp, j are Jordan's changed of the pencil at the eigen value lambda naught, and cj naught and so on are Jordan derivative change for the adjoint operator pencils. What if the canonical change 4 is already selected, then the change 3 are Jordan of the adjoint operator are defined in a unique way. And here I shall present the result which I proved in 1981. Certainly it is connected with 0 and 1, which I formulated before. And why I did present this lemma? Because it is essentially used in the proof of the factorization theory. I proved this lemma not only to improve the minimality of Keldysh derivative chains, but to prove the factorization results. So let GQ is operator matrix with on the diagonal we take these operators, and B1 is this operator. You see, this is upper right diagonal has right diagonal form, and here the left diagonal form. Q is any number which is equal not and so on m minus 1. Then the following biragonality relations hold. GQ, or here I missed GQ applying to YJ, YKH, here the operator GK is applied to the y h upper index and j and k is lower index. Certainly, these Bernoulli relationships prove the minimality of Keldysh derivative chains in the space of in the trace space which I defined before. This is quite certainly not a simple proof of this lemma, and certainly I will not discuss how to prove it in this talk. And, historical remarks are the following. In some sense, I almost finished the first part about general problems, general operator pencils, but it has a long story, and it was originated by the work of the paper of Keldysh in 1951. In this paper, he only announced results, but it will prove. But in 1971, he proved he proved it. He was president of Russian Academy of Science, but he retired from this position at 1970. But certainly there were mathematicians which did help him to write down the results. These results were in different form, and the main difference was the following, that he proved minimality and completeness only for the case of Keldysh pencils, not in the space of traces, which I introduced before, but in the space of copies, HM, of M copies of the space HM. It was not how to say it, not very good. Why? Because actually Cauchy problem for the equations of the form which I discussed before should be, the initial data should be set in the spaces with different topology, because the initial data u of naught equals, say, phi naught, certainly then u prime of naught x equals phi 1. Certainly phi naught should belong to the space of the with strong topology. Its derivative should belong to the space with weak topology, second derivative with weak topology, and certainly it is clear. The introduction of all these trace spaces was given on only in paper by myself in 1989. Certainly many mathematicians were occupied with pencils of order 1 because the theorem was absolutely new for linear equation. For linear equation with operators which for equations which include only A0 and A1. Certainly many interpretations were given, but I pay attention here that the trace spaces were introduced in 1981, and orthogonality relationships which are important in the future also were proved in 1981. So I come to the definition of hyperbolic equations. The equation is hyperbolic if the Cauchy problem for this equation is correct. Let us consider operator pencil of this form. The corresponding operator equation, we have the corresponding equations if lambda will change by d over dt. Here, f is self-adjoint and uniformly positive, as well as the operator c, but b is subordinated to c in the sense of quadratic forms. This is subordination in the sense of quadratic forms, where c is a constant. Moreover, we assume that B is accretive. It means that this condition does hold. C is unbounded operator. And theorem 2, excuse me, I missed this printing error. Theorem 2, let A of lambda be hyperbolic pencil, so these conditions are do hold, and S equals, you see, here I assume that C is positive, but in the next theorem, C will be not positive. So I denote the modulus C, the operator S, that's a square root of the modulus C. Denote H beautiful is this space. You see, again, we have different topology and assume that the domain of B intersection which H1 is density in H1. Then for all initial data, there exists a unique solution of T of this equation such that these conditions hold, and the solution U of T and its derivative U prime of T are uniformly bounded for T greater than 0 in the spaces H1 and H correspondingly. It means the following, the estimate does hold. If in addition the operator B is sectorial and uniformly accretive, then the right-hand side of the last estimate of this estimate can be replaced by M e to the power epsilon minus epsilon T. So solution is actually exponentially decaying. It follows from the statement of this theorem that if we consider the family which put into corresponding the initial data U0, U1 solution of the problem, which does exist. Then this family generates a C0 semigroups, a strongly continuous semigroup in the space H plus H. Its generator must be a linearization of the pencil A of lambda. So this generator can be constructed in the explicit form. The study of hyperbolic operators takes, takes the origin from the book of Lord Kelvin and Tate, which was written in 1868. For matrices, when F is equal to identity matrix and C is positive matrix. And B has the form with D greater than 0. So B is an accretive matrix. The idea to prove to the pencil A of lambda, we put into correspondence a linear pencil. So this matrix operator is denoted by bolt T. And one can check that operator T acting in the space H1 plus HF, where HF coincides with H, but the norm is replaced by the equivalent norm, this one. So in this space, we can reduce quadratic operator pencil to linear one. And this operator, we denoted by bolt T, is an accretive operator. Its domain, the domain of T, is equal to this one. And we assume also that H1 belong intersection with D of P is dense in H in H1. The main problem is to prove, actually the main problem is to prove that it is a maximal accretive operator. My student Hrinev and myself in 2 or 4 found the criterion of M accretivity. This is the density of D of B intersection with A1 in H1, and the subordination of B to C in the sense of quadratic forms. So if we, our conditions of theorem do hold, then the operator T, which is constructed here, is a maximal accretive operator, and so it is. It does it is a generator of a contraction semigroup, not only C0, but the contraction semigroup. Here, theorem is new only with in this. If we, in 15 years ago, we had more than 15 years before, we did work with F equals identity and different restrictions for the operator D. So in some sense, this theorem is new because we change identity to the operator F. Actually, starting from the book of Lord Kelvin and Tate, the work with this pencil was carried out by many mathematicians, in particular by Zayas, Huang, Wimmer, Lancaster, Marcus, Matsayev, Miloslavsky, Zefirov, Pivovarchenko, Trun, Trigiani, Valery Vasilievich Kozlov, yesterday, many others.
Sorry,
Our achievement that
sorry for interruption. As a chairman, I must say that time for discussion has started. If you need 2 more minutes to finish, no problem, but well, it's
yes, okay. I will take about 3-4 minutes more, and I will finish. So the main achievement was that to prove that we did prove the maximum accretivity of this operator matrix, because in the previous papers, much more general, much more strong assumptions were assumed. Actually, new theorem is also that that we can work not only with positive F and positive C, but we can assume that the indices of inertia indices of this operator C and F are finite. Indices of inertia, it means that the number of negative eigenvalues of these operators F and C are finite. And in this case, we can reduce our pencil to this one. Identity is a Britain arrow, which we denote, this operator we denote as before by T, and this operator we denote by W. If indices of inertia of operators F and C are finite, then this operator is accretive in the Pantriagen space, where G C is this operator and GF is this operator. And then we have accretive operator in Pantriagen space. And in this case, we can prove approximately the same. However, one has to change to make some additional to change some statements. And finally, the main part is elliptic problems. They have this form. C is positive. C is positive. You see here we change the sign of C, and here, as an example, we consider a Helmholtz equation in the semi-strip x belonging to 0, 1 and y more than 0. The symbol of this operator is this one, where S is the second derivative and D of domain of S is Sobolev space with some boundary conditions U. In this case, the radiation conditions can be formulated as follows. One can look for solutions of the problem. One can look for solutions of the problem as y tends to infinity. In this form, where lambda k belonging to the imaginary axis, so these waves are evanescent, oscillating, and U0 is a decaying solution. These conditions are called, these representations means that we consider so this representation means radiation conditions. And for Helmholtz equation, certainly imaginary positive eigenvalues correspond to the evanescent waves with positive group velocity. But Sommerfeld solving the Helmholtz equations assumed that evanescent waves have to correspond to positive imaginary part. But actually, Mandelstam proved, Lamb discovered the waves which have imaginary positive imaginary eigenvalues, but the group velocity of these waves is not positive. The Mandelstam supposed that proposed that we have consider evanescent waves with positive group velocity, and positive group velocity is defined by positivity of this number, where phi k is eigenvalue, eigenvector corresponding to the eigenvalue lambda k. So, according to Agman-Lein definition, elliptic pencil is on the imaginary axis. We have to assume this estimate. And theorem 2, which is actually the main one, is the following one. Assume that one of the conditions holds. A of lambda is elliptic, and the order of the operator C is greater than 2. The operator B admits a representation k to the s to the power s1, where k is k1 with k norm k1 less than 2, and k is a compact. Then the operator A of lambda admits a factorization. This one, excuse me, this factorization, where V is a bounded and boundedly invertible in H, and the spectrum of the operator of this divisor, right divisor, operator Z, lies in the open left half plane. Moreover, at the imaginary axis, it has finitely many eigenvalues which correspond to the waves with positive group velocity. The operator Z is a generator of a holomorphic semigroup in the spaces H zeta for all zeta in the segment 0, 1. Such an operator is unique. So the Mandelstam conjecture was the following: that equation has elliptic equations has with radiation condition at the beginning has a unique equation, has a unique solution, and certainly this result does prove the Mandelstam conjecture. History is very difficult, but I
thank you for
that this theorem is new, actually. Yes, excuse me. This is.
Thank you very much.
Yes.
Unfortunately, we don't have time for questions, but please, if you have 1 more hour in your schedule, we can give you time for questions for your talk after the next talk. So
after the next one. Okay, fine.
So please, stop your screen sharing.